Hi students, this is Mr. Yao. Today we're going to talk about 7.3, where we will learn more angles that is being formed by secants, tangents, and chords inside a circle. So first, tangent and chord theorem. This one is saying if we actually have a tangent line, which is right here, we're going to have this point of tangency. We're going to make a chord from this point of tangency. After we have that, we're going to cut this circle into two different arcs. And there's some kind of relationship between the angles formed by the chord and the tangent line and these arcs. So if you see the right side of the tangent line and this chord is forming angle 1 and the arc within is arc AB. The theorem says angle 1, the measurement of angle 1 is actually half of the measurement of this arc AB. And also if you look at the left side, you'll see the chord and the tangent line, the left side of the tangent line form this angle 2. And the arc being formed is arc BCA, which is a major arc. And the relationship is angle 2 is half of the measurement of BCA. Now let's actually use the theorem for some examples. Example 1. You see the left side is angle 1, and the arc is 130 degrees. So we're just going to need to half it, which is 65 degrees. That's example 1. Example 2, KJL, which is this major arc, and you see this angle is right here on the same side of the chord and the tangent line. We're going to need to use 125 degrees, multiply that by 2, which gives us 250 degrees for the measurement of the arc. Example 3 is asking for arc RT, which is actually on this side. You have two different ways to do it. Either you can use 90A to find this major arc on that side and then use 360 to subtract, or because this tangent line is a straight line, we can actually get the other side of the angle is going to be 82 degrees. And arc RT is actually formed by the chord and this side of the tangent line. So we can just use 82 times 2, that's going to give us 164 degrees. If you actually want to prove this, we are going to need to use the center and actually form the central angle, because the measurement arc is basically this central angle. And because we actually have that, we actually have 90 degrees here since that was a tangent line. And you can use these relationships because that's an isosceles triangle. These two angles are actually the same. You can actually use these, and the right side is forming 90 degrees. The angle relationship is going to be enough for you to prove tangent and theorem and chord theorem. Next, if we actually have intersecting lines inside a circle, with the circle, we actually have different kind of forms. First, we can have the intersection on the circle, like the first one, or inside the circle, the middle one, or outside the circle. And because of that, we can actually have some more angle relationships we can use. First, if the angles are inside the circle, so if the intersection is actually inside the circle, we're going to form some angles. So basically, we have two chords that actually are intersecting inside a circle, and we're going to have some angles. The theorem is saying this angle 1, and if you look at it, also have the vertical this side, vertical angle on this side, they're the same. This angle 1 is half of the arcs that they're facing. So angle 1 is facing this side of the arc, the red one, and also the vertical angle is facing the blue arc, and the measurement angle 1 is these two arcs add together, then half of it. As for angle 2, that is going to be this side of the vertical angle with angle 2, and the arc would be BC and AD. So we add the arc together, and half of it, that's going to be angle 2. That's what the theorem is saying. Now, if we actually have points outside, we can have more different kind of lines. So we can actually have a tangent and a secant, or two tangents, or two secants, and they'll actually form more angles that we can use. So for this theorem is actually saying, if we have an intersection outside the circle, no matter what kind of lines we use to actually form some angles, this outside angle is going to be having some kind of relationships with the arcs that's being cut by the two lines. So you see it's always the red, the further away one, subtracting the closer one, which is the blue one. So BC minus AC. And this one, the red one, is PQR minus the closer one, PR. And this one is the further one, XY, minus the closer one, WZ. They subtract, and half of it, that's going to give you this angle actually outside. That's being formed by the two lines. Now let's actually use one of these cases to prove the theorem. We're going to use the one that's actually inside. So if we say chord AC and BD are intersecting, then we're trying to prove that angle 1 is half of arc AB and arc CD combined. Okay, the first step, we're going to say they actually intersect at this point E. So when we actually want to name something, name a point, that's what we're going to do. And let's actually look at the logic. So the line is already connected. BC is connected. So if you look at the arc DC, I can kind of see, oh, well, I have this angle right here. That is the inscribed angle of that. And also then you look at arc AB, I can see this side is actually the inscribed angle. So when you first look at angle 1, you can kind of see it's outside a triangle. And if you recall, that is related to the triangle exterior angle theorem. So that's kind of what we're going to use. So now let's go forward. Angle 1 is the same as angle DBC plus angle ACB. If you forgot, it's basically saying if we have a triangle, this angle outside, like angle 1, is going to be the sum of the other two angles add together. Which makes sense because 2, 3, and this 4 adds up to 180, or 1 adds up to 180. If you just kind of do substitution, 1 is the same as 2 and 3. So that's triangle exterior angle theorem. And that's our second step in the proof. After that, we can actually also know, just like I was mentioning about the inscribed angle, DBC is actually facing the arc DC, so it's 1/2 of DC. ACB is actually facing AB, so it's 1/2 of AB. That is the reason is measure of an inscribed angle theorem. After that, we can actually put them together. And angle DBC and angle ACB is actually the same as angle 1. So I just replace DBC with 1/2 DC. I just replace ACB with 1/2 AB. And that next step is substitution property. Last thing, I just take out the 1/2. So distribution property, I have 1/2 measurement of DC and 1/2 and measurement of AB combined. That is going to give me angle 1. As for the other cases, the proof is actually very similar. We're still going to use inscribed angle and arc to form relationships. Now let's have a look at how we use the theorems. So number 4, x is right here and the vertical angle is on the other side. You see the vertical angle is actually facing the 130, x itself is facing the 156. So x is going to be 1/2 of 130 plus 156, which is going to be 1/2 times 286, that is going to be 143. And since the real symbol is already there, I can just leave the number. X is 143. Number 5. Now x is outside, and it's going to be the further away arc subtracting the closer arc. X is going to be 178 minus 1/2 times 178 minus 76. That is going to be 1/2 times 102, which is 51. Degree symbol is given, so I just need the number. X is 51. Next, example 6. This time we're not given exact numbers, but we actually can form the same kind of equation. Further away arc subtracting the closer one, so 3x minus 2 minus the closer one is x plus 6. And the whole thing is going to be multiplied with 1/2, which is this angle, 34 degrees. So actually going simplifying, that's going to be 1/2 times, that's 3x plus 2, 3x minus 2 minus x minus 6, which is going to give me 2x minus 8. So multiply 1/2 on both sides, or you can distribute the 1/2 in. Either way, 68 equals 2x minus 8. After solving, x is going to be 30. Last one, example 7. So this 102 is given right there, which means I know this side is also 102. And since the whole thing is 360, I can actually know these two vertical angles. That together is 204, so I can use 360 minus 204, which is going to give me 156. So each side is actually going to be 78 degrees, right there. 78 degrees. So I can have 78 degrees, which equals to 1/2 of y plus 95, which is going to be 156 degrees equals y plus 95. So after solving, my y would actually be 61. Degree symbol is given, so y is just 61. The reason I actually try to find the 78 is because y and 95, they're at the angle that are facing them are here, not the 102. That is everything for 7.3. Thank you.